All right, we're going to start our third chapter, and it's on polynomial functions. Today what we're going to do is figure out what a polynomial function is, what it looks like, what are some patterns and trends that we can use to figure out what the graph would be, what are the x-intercepts, y-intercepts, things like that. So this title page, it shows a complicated polynomial function, but you can see basically it is a combination of things we've already done before. You've already done linear functions, which were just a straight line. You also did quadratics in Math 20, which would be curve shapes. Now what we're going to look at is what happens when we get to a third degree, fourth degree, fifth degree, and so on polynomial. So let's start by going through a few characteristics first. So the first thing is a polynomial function is basically anything that has a variable with whole number exponents. So that means we have to have an x squared, an x cubed, an x to the fourth, something along those lines. We can't have negative exponents. We can't have square roots or fractions or anything like that. It's basically, it just has to be whole numbers. So we have x to the fourth in this case. We got x to the 3. This would be x to the 1, even though the 1's not there. We know it's there. And even a whole number like 2 is technically still has an x, but it would be x to the 0. Okay? So all four of these terms do have whole number exponents. Coefficients can be anything. They can be whole numbers, fractions, square roots, anything that we can see, positive, negatives. We got all kinds of different things going on, so that doesn't really matter. What we're going to do is classify the degree of the polynomial as being whatever the highest exponent is. And in this case, it's the 4. We have x to the fourth. That's our biggest. We'd say it's a fourth degree polynomial. The leading coefficient is the number in front of that highest degree term. So in this case, the 3, the positive 3 in front is our leading coefficient. We don't really care so much what the number is, but what we're going to find out is whether it's positive or negative is going to make a difference. And the last part of the thing that we want to identify is our constant term, which would be the very last term in this case, which is negative 2. It has no x value. And that constant term, if we remember from earlier math, that's going to give us the location of our y-intercept. Okay, so let's go through each different type of function that we've already learned about, and then we'll start adding a few new ones as we go. So a constant function is basically a degree 0. So that's an equation like y equals 4. Because we have no x value, we have no slope of the line, and we would just get a straight horizontal line that goes on and on forever through y equals 4. So our constant is only 4, so that is our y-intercept. Okay, our leading coefficient in this case is also 4, which is positive, so that means we have a positive line, so it's above the x-axis, and you can see over here when we have y equals negative 2, we have a constant line going through negative 2, but because it's negative, it's now down below. Constant graphs we're not going to really do a lot of, so they're not really that big of a deal, but they do show up once in a while. Okay, the next one is one that you should recognize from Math 10. So in this case, when we have a linear graph, that's a degree of 1. So that means we have a highest degree is 1 on the equation. So now to graph these, we graph them and we can see there's a few different trends. Our constant is 4, so that's our y-intercept. And because our coefficient is, in this case, it's a positive 1, we know that it's going to have a slope in the positive direction. Okay, we don't necessarily know too much other than the slope is 1, so we could actually sketch it out, where over here we've got a slope of negative 2, so that means our line is going to go slope the other direction, and the negative 3 is telling us our x-intercept. So based on just those two bits of information, you can usually sketch out a graph fairly accurately. So if we had a graph of y equals 4 minus x, okay, the order doesn't matter, we still have a degree of 1, and our leading coefficient would be negative, so we know it's got to go through 4, and it's got to have a negative slope, so we know the graph would look something like that. Okay, the next equation that you've done before is quadratic, so that's our U-shaped kind of graphs. A quadratic occurs when we have a second degree, so we have to have an x squared in the equation. And if it's a positive leading coefficient, so we have a positive out front, that's when we get our U-shape. And we can see our y-intercept is at 4. And the minus 2x in the middle really doesn't do nothing. It's just going to sort of indicate where that U shape is. So if I change that number, it may move the graph something like that, or whatever. Okay. The next one, you can see we still got a quadratic, still degree 2. Our y-intercept is at 1, but now we have a negative out front, so that means it's going to be a downwards U-shape. Okay, so our new one now is a cubic function, and a cubic function is going to be sort of a combination between linears and quadratics. So you can see now we have degree 3, we have a positive out front, and we have an y-intercept of 4. So we know it's crossing at 4, and because it's degree 3, what we see is we actually get sort of like a quadratic. It starts, goes up, but then we get this S-turn, we get sort of a change in direction. The key thing with the degree is if you have a degree of 1, we think of it as just sort of being one line or one direction. If we have degree 2, we have a curve, so we're kind of going up, and then we change and go back down. So that gives us sort of 2 different directions. With degree 3, you can see we're going up, we turn and come back down, and then we turn and go back up again. So that gives us 3 different directions. Just like linear curves, if we had a positive straight line, that was a line that was angled up to the right. And for a negative, you can see if we had a negative straight line, we had a line going downwards. So when we have a negative cubic, it's sort of the same thing. You can see it's starting up in the left quadrant, or in quadrant 2, and ending down in quadrant 4. So the negative is just going to tell you which way it's going. Our degree 3 means we got 3 turns, so went down, then up, and then down again. So we got our 3 turns. And in this case, we have no x-intercept, or y-intercept, so you can see that it's passing through the origin. One thing you got to be careful of is it doesn't necessarily have to cross the x-axis 3 times. We can see in this second diagram, let me clear all this, we have 3, because it's degree 3, we actually have 3 x intersection points. When we have a second degree graph, doesn't matter whether it's up or down, we usually have 2, not always. And when we have a linear line, we typically have 1. So degree 1 usually has 1 x-intercept, degree 2 usually has 2, degree 3 typically has 3. But not always, because we can see in this graph to the left, we only just have 1. So you could have 1, you always have to have at least 1. We could have 2 if the graph was down and it just touched it in one spot, right? So that'd give us 2 x-intercepts. Or we could have 3 like we have in the right diagram. So the degree typically is going to tell you how many possible x-intercepts there are, from 1 up to whatever the degree number is. So let's keep going and look at a 4th degree. So the name for a 4th degree is quartic, and a quartic function, we have 4th degree. You can see in this case we got a positive, and the rest of it stays the same. We have an intersection point of 2. So now, because it's 4, we're actually changing directions 4 times. This first graph isn't quite as obvious, so let's move to the second one first. We've got our negative, so we know it's going to be going upside down. And you can see we're going up. Then we turn and come back down, we turn and go back up, turn and go back down. So we've got to change a direction of 4 times. So this first diagram, it should change directions 4 times as well. And you can see the bottom here, we got this U shape at the bottom, so that one's obvious. The trick is we have sort of a little change right in there at the y intersection point. So even though it's not obvious, you can see we went down, kind of went back up a little bit, changed directions again, went back down. So that's our 3, and then our 4 coming back up. So the trick with these kind of graphs quite often is you're not always going to see the 4 or the 3 turns clearly. It's even possible I could draw an x to the 4th. If you just graph y equals x to the 4th, the graph looks just like a quadratic. So x squared, and then if you graph y equals x to the 4th, they're both going to be very similar. Y equals x squared is something like that. Y equals x to the 4th is just going to look like a skinnier quadratic. So it's not always going to show you all 4 changes. So typically, if we had a normal x to the 4th equation, it might look sort of like a w. But it could, because it's squished, it could end up being more like a U shape, like a quadratic would be. In either case, just like we did for cubics, we could have up to 4 x-intercepts. So we have, in this case, you can see we got 3, if it touched right in the middle. If this middle one went down a bit more, we'd have 4. We can see in the diagram on the left, we have just 2. And it's also possible we could have just 1. We could have a graph that does maybe something kind of like that. So we have just one intersection point, and it's also possible we could have 0, right? We could get a W-type shape that never touches the x-axis, whether it's right side up or upside down. The last one we're going to look at is a 5th degree, and it's a quintic, we call it, and it works the same way, except we get 5 directional changes. So you can see here we got one going up, one going down, back up again, back down again, and then back up again. So we get sort of like a 3rd degree. Like a 3rd degree would be just like that. So a 5th degree just has one extra change in the middle somewhere. But the rest of the rules are still the same. If it's positive, we're going to go upwards to the right. If it's negative, you can see we're going downwards to the right. And the y-intercepts, all that stuff is still the same. What you want to do now is sort of compare ones that are similar. So when we draw a 1st degree polynomial, we basically have a straight line if it's positive. So that goes from quadrant 1, or 3 to 1, so we're starting in 3 and going up to 1. If we had a 3rd degree positive polynomial, it would look sort of the same. So we'd just have a curve in the middle, so we'd have something like that. And if we did a 5th degree polynomial that's positive, it would do the same, except we'd get an extra bend in it. So 1, 3, and 5, they're all fairly the same graph. You can kind of think of it as like being a bendy rope, and if you just grabbed either end and straightened it out, it would end up just looking like a straight linear line. But if they're positive, they're all going to go in that direction. Your number of x-intercepts, remember for the linear we got 1, because it's degree 1. For a cubic, we could have 1, or possibly 2 if it touched in one spot, or possibly 3 if this graph curved all the way down. So we could have 1, 2, or 3 for a cubic. So linear is 1, cubic is 1, 2, or 3, and for a 5th degree, a quintic, we could have 1, 2, 3, 4, or 5. You could have any possibility. And it just depends on how it's set up. So let's suppose we want to do a quintic with 4. We could go up, down, and up. That's 3. And then the 4th would just touch in one spot. Okay, so you can have any number up to whatever the degree number is. If it's a negative graph, like a negative function, the exact same thing applies, except our direction is opposite. We're going from quadrant 2 down to quadrant 4. So if you had let's clear all this off. If we had a quadrant like this, but it was negative linear, it would be a straight line like that. If it was a negative cubic, we'd have one bend in it, something like that. And if we did a 5th degree, we'd have 2 bends, and so on. So you get the idea. Really, the only thing that's got to be careful of is the positive or negative to figure out which way it goes. So now when we do even degree ones, same sort of patterns apply, except we're just dealing with different quadrants. So if we have a positive 0 degree, so 0 degree, remember, was just a positive straight line that was above. So we have 0 x-intercepts, and we can see it's going from quadrant 2 to quadrant 1. If we have so that was our constant function, or 0 degree. If we have a quadratic, which was degree 2, remember if it's positive, it's going to go U-shape. So once again, positive, it's still going from quadrants 2 to 1 at the top. And we could have 2 x-intercepts, or if our quadratic was above, we'd have just 0, or we could have 1 if it just touched. So in this case, we got 0, 1, or 2 as possibilities for x-intercepts. And our last one is our quartic is degree 4. So it's going to be sort of the same thing, but this is our W shape. So if it's degree 4, it would look like our quadratic, but it'll have an extra bend in it. And once again, we could have 0 possible x-intercepts if it's above. We could have 1 if one of these touched. We could have 2 if both of them just touched. We could have 3 if one touched and one went down below. That would give us 3. Or if they all go down below, we could get 4. So that's what the x-intercepts are. Even odd degrees, it's 1, 2, 3, 4, 5, up to whatever the degree number is. For even degree ones, it's 0, 1, 2, 3, 4, depending on whatever it is. And positive even degree ones will always be from the top two quadrants. So it doesn't matter what kind of equation it is. If I gave you a positive x to the fourth equation, it's going to start in quadrant 2, and we'd get our W shape, and it'll end up in quadrant 1. If it's a negative, quadratic, or quartic, doesn't matter which one it is, it's going to just be upside down. So if we do a negative x to the fourth, right, it could end up being something like that. There shouldn't be any little zigzag in that line. It should be just a straight sort of W type of shape. Okay, so that's it for those. So this one's always going to go from quadrant 3 and end up in quadrant 4 if you go left to right. So that's it for the graphing features. So what you have to be able to do now is sort of look for features of these graphs and be able to match them to equations and so on. So let's go through this example. It says determine which equation is even or odd and determine the end behavior. So let's do that, just these top two first. So looking at equation A, we can see we got third degree, so that would be odd. And because we got a positive 2, we know it's going to be going in a positive direction, so we should get from quadrant 3 up to quadrant 1. Okay, if we look at letter B, we got a negative fourth degree, so we know that's going to be some sort of W shape, but it's going to go from quadrant 3 to 4, so it's going to be downwards. Letter C, we got negative fifth degree, so that one's going to be in the negative direction with a bunch of bends in the middle. And the last one is a positive x to the 4, so we know it's going to be upwards in a W shape. Okay, so that's the first two, just sort of helping you figure out whether it's right side up, upside down, and which quadrants it's going to go between. The next thing now, what we want to do is check out the number of possible x-intercepts. So if we got a third degree, that means it could cross 3 times, but it doesn't have to. It could be 1, 2, or 3. And if we have a fourth degree, remember that's going to be a W shape, could cross up to 4 times. So I got 4 there, but it could be 3, 2, or 1 as well, or 0. And same thing with fifth. We'd just get one extra one. If it was a fifth degree, it would have our extra bend in it, something like that. But remember, it could be up to 5, doesn't have to be. And the last part here is asking, does it have a max or min? So if you look at these graphs, if they go on and on forever, like A, it's going up forever and down forever, we don't really care what's going on in the middle. We would say it has no max or min. Even though these are little peaks in the graph, that would be a maximum just at that localized location. But in terms of the entire graph, we say no, there are no max or mins. So odd degree, 3, 5, 1, whatever, we typically don't have any max or min. Our domain and range would just be XER, YER for both. For even degrees, 0 to 4, we typically do have a max or min. So if you look at this B equation, you can see we have a maximum up there at about 30 or whatever it ends up being. Or if you look down at this one, we have a minimum at negative 50. So there are max and mins in this case. Usually our XER is still the same, but our Y now would be in this case greater than or equal to negative 50. Okay, so just be a little bit careful of those. Even degree, you usually have max or min. Odd degree, we don't. Okay, so our last thing on this question is, let's try to match the graph to the equation. So let's go through these. Here we have for A, we got a cubic, positive graph. So we know it's got to be going from upwards left to right, and we want 3 bends in it, or 3 changes in direction. We could have 3 x-intercepts. So I think letter D is the right answer because we got 1, 2, 3. So we got our 3 bends. It's positive, so it's going in the right quadrants. In this case, we only have 1 x-intercept, but we could get more if this dropped down. So A and D are a match. Let's look at the next one. So let's kind of do the one below it first. Let's look at letter C. So letter C is a 5th degree. So we should see 5 different bends. So it looks like A is the right answer because it's negative. So it's going to go in the opposite direction from this quadrant down to quadrant 4. So quadrant 2 to quadrant 4. And we should have 5 different changes. So 1, 2, 3, 4, and down again is 5. So that seems to be the best match for that one. Now if you look at B and D, they're both x to the 4th equations. Only difference is one's positive, one's negative. So the positive one should be a W shape upwards, so that would be C. And the D, the negative, should be a W shape going downwards, or like a big M. And that's it. Both of them you can see are 4. So there's one, this one's hard to see, it's 2, 3, and then bend is 4. Here it's more obvious, 1, 2, 3, 4. We got our 4 x-intercepts. So don't necessarily go by x-intercepts. Like this one had 4 for a 4th degree. This one only has 2 for a 4th degree. For letter A, we only got 3 for a 5th degree, and for letter D, we only have 1 for a 3rd degree. So x-intercepts won't tell you necessarily what kind of equation it is. Look for the bends or the changes in direction. That's a better way to identify. Okay, our last question we got here is a word problem. So this one's giving us an equation to model a number of pests on a field. So you have a number of mosquitoes or whatever it is, and you're going to spray a chemical. So we have an equation that's showing that. So the first thing you want to do is actually graph this equation. So on your calculator, type in negative 2t cubed minus t squared plus 3t plus 800. Okay, so if you type that in, you got to be careful because your calculator can graph p's and t's, but you just put in y equals minus 2x cubed. That'll be fine. And then the second part is to try to get this to show up in your calculator is going to be pretty tough because of this plus 800. So you're going to have to really zoom out your window settings, which is going to make it pretty tough as well. So probably in this kind of question, you're probably better off just to deal with the equation and deal with it mathematically. So part A is saying how many pests are there going to be after the spray? 3 minutes after the spray. So we're looking for a time of 3. So it's probably easier in this case, just plug in the negative 3 mathematically. So go negative 2 times 3 cubed minus 3 squared plus 3 times 3 plus 800. And just do the math on that. Or if you really wanted to, from your graph, you would have to figure out what the y coordinate's going to be when x is 3. So if you do graph it, you could put in second calc value of 3 and see what that works out to. So if you do that, we get an x of 3 is going to be at 746. If you do all of this on your calculator, you should get 746 pests. Okay, so it's probably easier just to type it in, like I said, and just figure out what the number is like that. Part B, it's asking how many pests were applied or were there before the spray was applied. So that's going to occur when time 0, right, before we start to do anything. So you can, once again, you can put 0 into the equation, but we can see that wherever there's a t, that's going to equal 0. So basically what we're looking for is our y-intercept, which would be 800. So that means we started with 800 pests. We start spraying it. So after 3 minutes, we were down to 746. Now the next question is, what's it going to be after 8 minutes? So if we do this calculation, put in an 8 for the t, so do all of that and figure out what it's going to be. We actually get an answer of negative 264. So does that make sense? Can you have negative 264 pests? No. So in this case, it doesn't really make much sense to figure out what the 8 minutes would be. In this case, it might be better off to figure out the x-intercept. So if we figure out the x-intercept from your graph, that occurs at 7.3. So what that means is at 7.3 minutes, all of the pests are dead. So, really the negative part of the graph in this case doesn't really apply. So even though it's a cubic graph and it's actually probably, doing some sort of weird graph, and it's negative, so we know it's got to be going downwards, so it might be a graph something like that. Really, we don't really care about the negative part because you can't have negative time, and you can't have a negative number. So you can't have negative pests or negative time, so really we're only worrying about the positive portion of the graph. So you can see that we would start at 800 in terms of our starting value, and then at 7.3 minutes, we would have 0 pests left over. So that's kind of all we're really worrying about in terms of the graph. So with real life problems, you got to be a little bit careful in terms of what actually makes sense in the context of the question. And that's all.